start with your presentation. Okay, cool. Okay, so welcome everybody to the webinar of today. That's the first webinar of the session 2022-2023 of the LMFL Fluid Dynamics webinar. And the speaker of today is Alexandros Alexakis. He will talk about intermittency in the inverse cascade of two-dimensional turbulence. And as usual, I briefly introduce the speaker and then I give him the floor. So Alexandros Alexakis is currently Director of Research at the Laboratoire de Physique de l'École Normale Supérieure in Paris. He got his PhD at the University of Chicago in 2004 and worked as a postdoc in the Advanced Study Program, ASP, in the National Center of Atmospheric Research, NCAR, at Boulder, Colorado, US, as the Observatoire de la Côte d'Azur, Nice, France, and Laboratoire de Physique Statistique of the École Normale Supérieure. His research interests lie in the field of turbulence, MHD turbulence, dynamo theory, and their astrophysical and geophysical applications. So it's with great pleasure that I leave the floor to Alexandros Alexakis. So Alexandros, I stop sharing my screen, and you can start sharing yours.
Okay. Sure. Okay, we're all set. Okay, thank you, Francesco, and thank you all, everybody at LAIL, for inviting me to give the seminar. I will talk about the work done recently with some colleagues from Athens, George Sofiadis and Ioannis Saris, that was done in the last year. And it's about intermittency in two-dimensional turbulence. And I will explain what I mean because it's a little bit provocative as a title, but I will explain soon. So it's about turbulence. I'm not going to give you a big explication why it's important. It's met everywhere. I will only make one point that more often than not, the flows that we meet, the turbulent flows that we meet in turbulence are far off from the homogeneous and isotropic description of turbulence that we usually meet in the classroom. So we keep that in mind, and with that, I'll proceed in explaining exactly a few words about the homogeneous and isotropic turbulence. So when we talk about that, homogeneous means that every point in space has the same statistics as everybody else, every other point, and any direction is equivalent to any other direction. So we're going to consider in most of talk periodic boxes, so we don't care about boundaries. And we're going to be using just the Navier-Stokes equation that we all know and love. So the first description, well, this one of the first descriptions of turbulence can be traced back perhaps to Richardson, where he gave this notion of hierarchy of eddies. So that you have large eddies that self-interact to create smaller eddies, and those eddies will create even smaller eddies, and so on and so forth, up until those eddies are so small that viscosity is very effective at dissipating them, and everything dissipates. And that's the famous poem that he wrote in 1920. Okay, so then after Richardson, we have Kolmogorov, who I guess gave the first quantitative description of how this transfer of energy from large scales to small scales happens. So where you could show some properties about the third moment of the correlation function of the velocity differences, and that's show that it has to be linear with respect to the distance of the 2 points and proportional to the energy dissipation rate. And in 41, he took it a bit further, saying that, well, if that holds for the third moment, if the flow is self-similar, which is a very logical assumption to make, at least at that time, then she could predict all moments, and the second moment would be proportional to the distance to the power of 2/3. And that's something that agreed very well with measurements at that time, at least. We can say the same things in spectral space, in which case we can calculate the flux. That would be something equivalent to the third moment in real space of the velocity differences. And the statement of Kolmogorov would be that there is a range of wave numbers where the flux of energy is given by this expression here, where this guy is the filtered velocity field, so that all wave numbers smaller than this wave number k are set to zero, larger than this wave number k are set to 0. So that expression has to be constant and equal to the energy dissipation rate. And again, the equivalence with the previous statement is that the energy spectrum will become proportional to k to the minus 5/3, something that also been verified in many experiments and numerical simulation since. And we don't have to stick only on the third and the second moment. If the flow is truly self-similar, which means that if I zoom in, I see the same thing, same statistics, not the same flow, but flow with the same statistics, it will imply that any moment will scale like the distance between the points to the power p/3, where p is the moment that I'm examining. So that was in 41. And if that was true, we would be finished with turbulence. If that was true, we basically would understand everything. It was only a matter of maybe calculating some non-dimensional coefficients, proportionality coefficients that enter the problem. However, it's not true. And what lots of measurements have shown in the last 80 years now is that the PDFs are not self-similar. So if you look at the PDF of velocity differences to large scales, you might start with something that looks Gaussian, of course, in a Gaussian way, of course. But as you move to smaller and smaller scales, large scales appear, and the distribution looks far different than Gaussian. I forgot that people in the but don't see my. So the structural functions are not follow the prediction of having an exponent p/3. And if you plot them as a function of the exponent as a function of p, we have this exponent zp here, you get a curve that is not a straight line as self-similarity would have implied, but it curves down. And that is intermediate, what is probably called intermittency. And the reason why this happens, the explanation has been put forward by Kolmogorov himself also, and a lot of other scientists, is that this picture of Richardson is not exactly like that. So not the eddies that are generated through the cascade process do not fill space as is shown here. This has been taken from the Frisch book. So I should pay attention to that, but it's more like this. So that the large eddies will generate smaller eddies that will be less space filling. And that process will continue, that they will generate even smaller eddies that are even less space filling. And this process will continue up until a fractal set, or a multi-fractal set to be more exact, the energy will be concentrated in a multi-fractal set in the domain up until it's dissipated. And this is something that is being visualized in numerical simulations that is very clear. Okay, so that's the status of at least what I can present in 5-10 minutes of what happens in three-dimensional turbulence. How about two-dimensional turbulence? So in many cases, we live in 3 dimensions, but in many cases, the flow cannot be approximated as being 2-dimensional. The flow in a soap field is a very good example of that, but also the oceans and the atmosphere to some approximation and for some scales can be modeled as two-dimensional turbulence. So if we move to 2 dimensions, what changes is we can write Navier-Stokes in terms of the vorticity, which is called W here, out of plane vorticity. And there is an extra quadratic invariant for the inviscid system, being the entropy. And that appears to play a very important role in the dynamics. And the difference is that in 3 dimensions, we have motions that take vortex tubes and shear them. And because you do that, you make them longer. And because volume is conserved, it means the cross-section area has to be smaller. And because the flux of vorticity is being just affected by them, it means the flow has to spin faster. So by doing that, you transfer energy to smaller eddies. So you end up with having this cluster of many small eddies that vortex tubes that fill out the whole domain. And that implies the transfer of energy to the small scales of large wave numbers and the Kolmogorov spectrum that we know. In 2D, things are different. We cannot have this kind of motions that I described before. We have vortex patches in this case, that the only thing you can do them is shear them like that. And if you do that, I mean, the area is conserved, of course. So the flux remains the same. What is changing is the length of the circumference over here. And because the vorticity is the integral of the velocity across that, by making it longer, it means that the velocity has to go down. So that means that when I do that to small eddies, the eddies lose energy. So if they lose energy and energy is conserved, it means that the larger eddy that sheared this smaller eddy has took its energy. So energy has been transferred to larger scales. So instead of having a forward flux, or a positive flux towards the small large wave numbers, we have a flux of energy towards the small wave numbers. And we can generate large structures like this. So all these were put into what is known sometimes as the BLK theory of two-dimensional turbulence, named after Robert Kraichnan, C.E. Leith, and Batchelor, put forward all these predictions. And that led to a K minus 5/3, but now for the larger scale larger than where I inject energy, while the entropy cascade is forward, generates a K to the -3. And that's our understanding of two-dimensional turbulence. Now, even further than that, so what was shown that in the reverse cascade of energy for two-dimensional turbulence is not intermittent. It's not intermittent, and when we look at the PDFs, that was work done by Boffetta, Celani, and Vergasola, they get very nice, close to Gaussian PDFs. They're not Gaussian. There are different because if they were exactly Gaussian, the flux would be 0. But there is small deviations from Gaussian, but they're Gaussian and they do not change with scale. So if we plot the structure functions that is shown here, and they are normalized by R to the P/3, they become flat. So that's the fourth and the sixth structural function for a two-dimensional flow. And there is a reasoning why this happens in two-dimensional turbulence. So suppose we have a bunch of eddies, small-scale eddies, and we have some extreme eddy over here. And then there are some larger eddies that interact and absorb energy of all these eddies. Then this guy over here that had some excess of energy will only see the average of those. So the difference between the red and the blue here will be stronger than what we would see in the largest eddies between the pink and the cyan over here. So the way that inverse cascade works in 2D, it kind of takes an average. So the law of large numbers says that things will start to approach Gaussianity because you just add many terms. At least that's hand-waving term explanation of why we don't see intermittency in two-dimensional turbulence. So in 2 dimensions, now the flux is from small scales to large scales, goes up, so it should look something like that. Of course, when we draw this picture, we do inject everywhere here. So the question I'm going to put forward in this talk is, can we have that? Can we induce intermittency in the system if we don't inject everywhere in my domain, but we inject energy only in a fractal set in my domain? That is the question, and that's what I will try to answer. Okay, so this is the setup that I'm going to be doing. I'm going to consider square box, a square, with periodic boundary conditions. Navier-Stokes equation, I'm going to introduce a hyperviscosity term, so this alpha term over here, which will dump any energy that arrives at the larger scale of the system. That's a technical trick just to remove this energy, otherwise it will pile up into a condensate. Sorry, spelling mistake. Nu is the viscosity, alpha the hyperdissipation, L is the domain, and I'm going to use a forcing at some small scale that I'm going to call LF that has this kind of form. So I give it some general shape that I will describe in detail in what follows. And I'm going to move it around in space randomly in a slow random walk. So I want that random walk not to be much slower than any other time scale here. Just so that every point is equivalent to the other, if you look at it at very long time scales. And I'm going to multiply it with amplitude AT that is delta correlated in time. Gaussian delta correlated in time. So that will impose the rate that I'm injecting energy in the system. And it's going to be given by epsilon. I will name it. And we will also would like that the forcing length scale LF is much smaller than my domain L, so that we have space to have an inverse cascade. So let me proceed. So the simplest forcing in the forcing that everybody is using is forcing wave numbers in a particular band of K. So all wave numbers between some KF and some KF plus delta KF will be forced with random phases. In this case, it makes no sense to move it around because it's already random and changing in every time step. So that's the classical forcing used in almost all two-dimensional simulations that I know. And that corresponds to, since we are forcing everywhere, it corresponds to a forcing of dimension 2. So that takes care of dimension 2. The other simple thing we can do is dimension 0. So dimension 0, what does dimension 0 mean? It means points. So we will be putting 8 points in my domain, randomly placed. And by point, it's not exactly a point, it's actually a Gaussian that has a width of LF. And then this forcing pattern, I will be moving it randomly in space. It's a very slow random walk. And at the same time, it will change values to positive, negative values. So I'm fixing the energy injection rate. On top of that, I should mention that it's fixed so that there is no mean vorticity injection at my domain. So you will see that there are 4 blue and 4 red dots here. So at any time, there's no mean injection of vorticity. So that takes care of dimension 0. Another simple example will be dimension 1. So instead of points, we have lines now. So again, I put 4 vertical lines and 4 horizontal lines. 4 blue, 4 red, so mean vorticity is 0. And they have a Gaussian profile again of width LF. So again, the forcing is given by LF. The forcing length here is given by LF, but it has a different structure. And again, the energy injection rate is again the same and fixed. Now we move to the more difficult cases if we want to use a fractal dimension. So fractal is being different than an integer. So the simplest sets that I know is the Cantor sets, where you start with some segment and you start removing parts of it. Well, classically, it's done with a segment that you remove 1/3 of it. But here, because we are in periodic boundary conditions, if I remove 1/3, these two will still be connected. So instead, I consider a line like this, and I cut it in 4 pieces, and I remove 2 of them, 2 non-adjacent pieces. And then from what remains, I cut them again in 4, and I remove again 2, and so on and so forth. And I claim that this structure has dimension 1/2, and then you can see that because if you split your domain in tiny boxes and you count how many of these boxes, let's call them n, the number of boxes that we have, and you count how many boxes m have at least 1 point from that set, then if that set has dimension d, the number of m should scale like n to the d. Like if we are in a 2-dimensional plane, if I draw a line, the number of boxes covered by that line should scale like n square root of n, where n is the total number of points. Here we are in a little bit more complex structure, but this d will be the dimensions. So if we start with n equal 4, so that will correspond to 4 boxes here, only 2 of them have the set. If we split in 16 boxes, you will have 1, 2, 3, 4. If we go to 64, it will be 8, 1, 2, 3, 4, 8. And you can see that if we have 4 to the n boxes, then 2 to the n will be the number of boxes that have at least 1 point in my set. So if I solve for little n in terms of big N and substitute here, I will get that this construction scales like n to the 1/2. So this is a set that has dimension d 1/2. So that means that if I do something like that, I will have a forcing set of dimension 1/2. Okay. So here you don't see a lot of vortices because my vortices are quite big. Once I move up in resolution, they become quite more small, and there are many more of them. In principle, what I do, I put 1024 vortices along this line, and then I start removing in the same procedure that I explained before. So actually here there are more than 1 vortex here, it's just that they're so close that you cannot see them. You have to go to high resolutions where this is like a dot, and then you can see that there are more than 1. And of course, if you can do 1/2, doing 3 halves is just as simple. We have lines that are put along the 1 axis, and then you start to remove again in the same way. So we get 1/2 from here and 1 here, so that makes 3 halves. So these are the 5 forcings that I will be using. So I plot them here. So the non-dimensional parameter that we have is first is the dimension of the forcing. Then we have the Reynolds number, which since I'm only interested in the inverse cascade, I'm going to give it relatively small, it's around 10. Then I have a hyperviscous number, which I define it based on the box size L, so not the forcing length here, otherwise it will be much bigger. And I keep it around 20. So fixing this Reynolds number defined with a box size, it only means that I tune my dissipation. So when the energy arrives at the larger scale of the box, it starts to dissipate. So it produces a cutoff that is close to the box size scale. And then we have the only parameter left is the ratio of the forcing wave number LF to the box size, or the inverse, actually. And I'm going to be calling this lambda. And that I'm going to vary from 16 to 32 to 64 to 128. So 128 would mean that I could put 128 dots here, one next to the other, slightly touching each other. Just and accordingly, I have to increase the resolution, of course, every time I increase this parameter. So I'm going to be going from 512 to 4096 simulations. Okay, so we're all set up. So I can start showing results. So we start with the simplest things we can do. So energy spectra that show behavior close to k to the minus 5/3. It's not exactly k to the minus 5/3. The red line, which corresponds to d equal 2, is the closest to k minus 5/3. The others show some small deviation, which is understandable when we proceed further. And the energy flux, that is, we see these two peaks that are due to the viscosity, which is the Reynolds number is not that big, and then they reach a plateau as we move further. The d equals 0, it's fluctuating much more, so that's why you see this large fluctuation. And I should also mention here the dashed lines is the spectrum of the forcing. So the forcing for the red line, that's dimension 2, it's bounded in this region here only. That's easily understood. And this is what you get from the Gaussian profiles that we used. Okay, so let's see how the flow looks like. So this is the 5 cases that we look like, and below is the vorticity at the steady state of the problem we were looking at. First one is the classical behavior we see. There is a damping coefficient here, so no big vortex has formed. Here we see something close to that, but you can see that there is some differences and some more quiet regions than here. Here you even see these regions that are quiet that increase. And here we see already quite a different behavior. We have a lot of vorticity action in some regions in space and some very quiet regions in other places. And that's even stronger in the D0 case. These are simulations from 1000 square. So we can do better. So I'm going to show you movies now for 1000 still, we're staying. So this is dimension 2. So that's the regular case. And I have relaxed a little bit my damping coefficient at the large scale. So the large scale vortex has just started to form. So that's the typical behavior. You see small vortices. I mean, if I stop it, you cannot see any large scales there. But if I let it go, your eye can identify that these small eddies are moved in some coherent way at some regions, which implies that there is a presence of large-scale flows over there. Okay, so that's the typical behavior. You can find many movies like that on the web. And now we go to the d equals 0 case. In this case, it's well, one thing is quite different than what we had before. We have regions in space that are quite quiet. You have some places here. You can see this point here. There is a source vortex over there, and it keeps feeding it. And I think there is another one over here, if you can see it. So it generates small vortices that are being advected. And the end result is that you have these clusters of tiny vortices that move around in space, do not fully fill the space because they dissipate or get shredded as they evolve away from the forcing. But it's a picture that is quite different from what we were seeing before. It's strikingly different. And I remind that this also shows a behavior that's close to k to the minus 5/3 and a constant flux towards the large scale. Okay, maybe this is slow resolution. So let's move to higher resolution. So that's the largest resolution. Examine at 4096 and forcing wave number being at k to the 128. So very, very small forcing. And the picture you see something like that. So there are vortices, some big ones have started to form, but it's uniformly spread everywhere. This is for the d equals 0 case. We see also vortices here. They are clustered in some regions in space. Some regions in space are very quiet, like here, and some clusters over here. And overall, the picture between the two is quite different. I mean, when you look at spectra and fluxes, you don't see much difference. But if you look at the image, one can certainly distinguish between the two. So let's start doing some more quantitative estimates. So we stick to the two extreme cases again. D equal 2, everything looks close to Gaussian, and more importantly, it does not change as I change scale. So the 6 different lines that I showed here corresponds to calculating velocity differences at different distance r. So the d is equal 2 case, well, everything looks Gaussian. The width of the Gaussian changes, so this is normalized by the variance, but the shape does not change. So it is indeed self-similar. That's what self-similarity would imply, that everything does not change. I mean, the width might change, but if you normalize it, you see exactly the same thing. And that's indeed true for d equal 2. And d equals 0, it's not the same. When we start, well, at the larger scales, it's not so bad not so far away from a Gaussian, but as we move up, the tails become stronger, and the curvature around the 0 becomes much smaller. So definitely you cannot say that this case is proportional to that case. Here we have much bigger tails and highly more picked at 0 than before. So we lost self-similarity. So the so clear self-similarity that we see in the d equal 2 case has completely gone away in the 0 case, d equals 0 case. So we can also look at the structure functions, and again, the two extreme cases. D equal 2 is surprisingly proportional. I mean, the first time I saw that when I was doing these calculations, I went into the code to check that I didn't make a mistake and plotted the same curve 6 times. It's surprisingly one proportional to the other. And that's up to p equals 6. And if we go for the d equals 0 case, it's clearly not the case. I mean, for 1, we don't even see a p equal 1, we don't even see a clear power law. For 2, we see something that's different. And 3, it shows a clean power law. 4, there is a power law that's different than 3. Sorry, I should mention that here. Here I'm plotting the structure function raised to the 1 over p. That's why everything is self-similar. It's otherwise, of course, every p is bigger. Here I'm raising the 1p. So if everything was self-similar, then this should not change as I change p. So for the d equals 0 case, it becomes more and more flat as p is increased. So it means we have higher probability to have small scales to find any events. Okay, so that's good. Of course, you can put the question, okay, you force in a very intermittent way because you're forcing a very small region in space. So one can ask, okay, if you're forcing very in an intermittent way, maybe it's not so surprising that you see intermittency. But the important thing is here is not, I'm not talking about the tails here. I'm talking about the fact that you lose self-similarity. When I say intermittency here, of course, the tails has to be there, but the important thing is that you lose self-similarity. And that's what I'm going to claim that it's important here. So we want to see if this is something that persists as we move to larger and larger boxes. And this is in fact what we see. So the top panel shows the 5 different the kurtoses, which is S4 divided by S2 squared. So that will be delta U to the fourth power divided by delta U squared, average, and then squared. So if we have, if it was a Gaussian or self-similar signal, it would be a flat line. And indeed, for d equal to 2, more or less, it is a flat line. But as we increase d, it becomes higher and higher and higher, more peaks. And there is a range where this transition will take place. And the important thing is that as we move to larger and larger scales, so we decrease our damping coefficient in the large scales and move to larger boxes, this range is increasing. So if I move to a very large box, I will have a clear range where the kurtosis is changing with R. And that's the important thing. So there is a range where kurtosis is increasing as R is decreased. And so I can fit power laws in the structure functions to get the exponents. I'm not going to claim that this is a very good fit because there are strong fluctuations in 2D, is not so many data as you can. But the general shape is what you see in three-dimensional turbulence. For d equal to is a straight line, but as these decrease, it curves down. And it actually looks like it will even decrease further down. So it's not going to be non-monotonic. And with that, I will stop because this is the result. I want to just say that one can at least reproduce intermittency signals that one sees in three-dimensional turbulence in 2D if you force in a fractal way. And such a simple model can provide a test bed for turbulent predictions. So we have these models that work. Here we fix and control the amount of intermittency that we put in our system. So one can take models that predict something and test them in this system. And finally, this can be extended to more complex and more realistic or more closer to three-dimensional turbulence case if we use multi-fractal forcing. So multi-fractal forcing here, I used monofractal, so there was one fractal dimension, but in principle, I could add all 5 of them with certain weights in order to have something more complex creature than that. And with that, I'll thank you for your patience.
So thank you, Alexandros, for the very interesting talk, and maybe we can open the floor for questions. So there is.
Sorry.
Yeah. No, go ahead.
Hi, Alex. Very nice talk. I'd like to ask the question. It's tempting to say when you look at the intermittency anomalous exponents, is there a way where you could go all the way to Burgers? That is to say, above p equals 3, it becomes flat, and you have quasi-shocks.
I think that we can go even further on that. It's the numerics. I wasn't 100% confident, but they actually start to decrease after p equal 6. So that, of course, if they indeed decrease, that would imply that there is some sort of divergence in the field, which is not so obscure because you're really forcing it in a tiny region with the same injection rate as you do in the other cases. So yes, the answer is you could go close to that after some function to be flat, but you possibly could even go further. So it will start decrease again. I'm not sure, so I don't want to make a clean statement. And so there are error bars here that I didn't put. So this is just preliminary work regarding the value of the actual exponent. So I don't want to comment on what exactly it would be as we go p to larger p.
Okay, I thought it was forbidden to decrease on a convexity argument, but I forgot it.
It means that it will there is a divergence in the flow. So it's written in the Frisch book. It's written that it's if it's decreasing, it would imply that the U max is diverging. So, but then again, I wouldn't like to give a precise statement about this if the P are flattening out or if they go up or down. I mean, there is some work to be done further, or to make a precise statement for the exponents.
Yeah, because remember the Srinivasan and other people argument that you need more accuracy. Of course, they're looking at small scale intermittency, but do you have an accuracy problem here?
For the well, I did show the exponents. It looks like that, and it looks quite flat as p equals 6, and as p equals 5, and then you start asking yourself, where should I fit the power law?
Okay, thank you.
So yes, I mean, I'm confident up to 5 or 6 for the large D cases. For the D equals 0, I don't want to push it too far with the statistics that I have.
Okay, thank you. I see that there is a question in the chat, so I will report it, and then we can ask someone else if he or she wants to participate. So the discussion says, in the discussion it's written, can you comment on entropy for this fractal forcing?
Well, I didn't really went to that regime. So my forcing was always, the Reynolds number I had that was always relatively small, between 10 and 20 or so, depending on the definition. So I really had no space to look at this bit of scaling of entropy in the forward cascade entropy regime. So really, I don't know. I mean, it's very likely that it will be affected, but I don't have any data to say how.
But I think it would be interesting to know if there is non-locality and interactions between the two ranges, entropy range and energy range. It's certainly a question that can arise, right?
Yes. Yes.
I think it'd be interesting to see.
It could happen, I agree. I haven't looked at it. And I haven't looked at it because it starts to become quite painful for very small d, or d equals 0, because the statistics convert very, very, very slowly. So that would have meant that I would go to very large grids, and that probably would never manage to converge the statistics.
Yeah, but you could make compromise like d equal 1/2 and you know, a factor 10 at large scale, a factor 10 at small scale. In 2D, you can do more than that. Anyway, just an idea, sorry.
Yeah, it's a direction that could be followed. I agree, but I haven't done it.
Okay, so let's see if there is someone else who would like to ask a question.
Christos has raised his hand here.
Go ahead, Christos.
Quick question: if you have some very high gradients in the field,
Yeah.
like perhaps the case of D equals 1/2 because you get some very high gradients, then these high gradients can actually force zeta p, which is independent of p, at some point. Would it be that you have some
If you have like a shock,
yes?
yes, that would probably make it look like Berger turbulence.
Yeah, so that's constant.
That would be constant. But we see something even stronger. We see a point. So if I mean, it's stronger than having just discontinuity or in the velocity field that would be a vorticity line. We have a point. Like the structure that we see here are point lines, not just line discontinuities.
Yeah.
So it could be stronger than that.
Okay.
I have a question, maybe.
Yeah, please go ahead.
I can ask a question, maybe, for Alexandros? Maybe.
Yes.
Okay. Okay. When you talk about fractal forcing, you just talk about the distribution of Dirac function of Dirac. It's like it's a Dirac vortices with a finite size, and this is when you show your spectrum. It's like it's like a Fourier transform of Dirac. Like here. It's like k to the power 2. I think it's a Fourier transform of the Dirac function of the Gaussian.
Yes.
But in my sense, when I speak about fractal, is the dependence between scale. Can you add not only one scale but different scale of vortices, maybe?
Because yes, yeah, you can do it, but I don't understand why I should do that.
For example, this for the what I see here, it maybe the forcing scale is close to 1. In fact, maybe you can add several size of the vortices, because for me the fractal sense is this. You have the link between all the scale.
The fractal structure of my set, I mean, it's like that. So what is changing is the distance between the vortices that has this property. It's not I don't have a hierarchy of vortices that are from different size L. I have the same size of vortices that their distance from each other is changing in that particular way. Because I do want that my forcing is the system is forced at the same length scale. I just want its properties in space to be different.
Yeah, for example, for the contour set, you can force for each scale, for the scale 1, the first iteration, the second iteration, the third iteration. At each iteration, you have a scale. Finally, you have the finite scale, it's your distribution of a Gaussian, but the first scale, the largest scale, is your first iteration, in fact. And so you can play with this scale, and maybe it's different because you play with the cascade, in fact.
Yes, so that would mean that I would inject energy here at all these scales.
Yes, exactly. And with a strong link, with a fractal link, all the dimensions are linked together with the same construction, the contour set, in fact, but for each iteration.
Yeah, but I really want that there is some range of scales where forcing does not play a role. And if I start injecting everywhere here, then I would never have that. I mean,
yeah, because
but the forcing.
Yes. At the end, you have a large scale, in fact, in your system, in your.
Yeah, if I do that, I will have forcing directly at the large scale. So that would obviously change the spectrum that I have. So not only the higher moment, but also the energy distribution. That's two.
Thank you, Alexandros.
Why is the flux so fluctuating as a function of k for only d equals 0, not d equals 1/2?
Because I had to restart the d equal 0 I had to change slightly the hyperdissipation coefficient because I realized it was dropping down here. So I had to restart it. So it hasn't run as long as the other cases. But it's also the one that clearly takes longer time to converge. I mean, D equal 2, 1 day I have a result, or maybe 2 days, or 4,000. The D equals 0, I'm running it for days and days now to get it to converge.
And the spectral exponent is different from -5/3? Seems to be different, right?
It's slightly different, but you said if S2 is different, then the spectrum will be slightly different as well.
But it doesn't depend on the dimension D.
Why do you say that?
It seems to be the same slope for all dimensions D except.
Well, there are many things that come into play. I mean, the differences are small. And then you need to also consider that here, there is dumping that maybe not be as efficient as it should. So that maybe we're starting for the bottleneck here. So you can see here, it's a pretty good fit here for the red line. And it slightly curves up as we move to large scales. So there's all sorts of parameters that need to be tuned, and maybe the tuning is not as perfect as we would like. So there are small differences that come into play.
Alexandros, I have a question which may be related somehow to a question which has been asked before regarding the fractality of your forcing. Here you are identifying basically the forcing by its dimension D, right?
Yes.
But you can link the same dimension D to different sorts of forcing, so it's not like a unique characterization of the forcing, right? So what do you expect it's gonna change if you change the pattern of your forcing, keeping fixed the fractal dimension?
If I change the pattern of the forcing,
yeah, I mean, if you construct, now you're constructing it as, for example, for dimension 1/2, you're constructing it as taking a counter set, but you can take a different sort of
fraction with the same dimension.
Yes, exactly.
I don't know, it could change. I mean, not necessarily the only parameter that plays a role here, but until you do it, we won't know the answer. I mean, until it's done, we won't know the answer.
Yeah, because I mean, maybe this could be related to your conclusions, in the sense that maybe there is a, call it optimization or kind of a control, not really a control parameter, but a control strategy such that you could get a 2D model that better approaches the 3D statistics, for example. Maybe if you produce your fractal dimension with a different sort of distribution of your vortices, you may get closer to the 3D statistics of the structure functions, for example.
Yeah, that's true. That's true. I mean, I just put the simplest thing that came into my mind when I was looking for fractal forcings to use. So better ones probably can be found, depending on what you want to optimize. When you say better, you mean you want something to be improved. So depending on what you want to improve, I'm sure that you can find a better forcing. I just picked the simplest that I thought of, at least at the time, and I could construct numerically. So yes, I would expect that better, more optimal forcings could be found, but of course I haven't looked for them yet.
Yeah, I was saying that this could be related to the question you had before, because basically you could think to a fractal dimension 1/2, which does introduce energy at more than one scale, and which goes, of course, you explained this goes against what you wanted to test, so that's totally fine. I mean, it's just like as far as I understand, you were trying to relate the fractal dimension to the exponent. I think it would be a possible, a nice question to ask. Is like this prediction can it be generalized when you increase the wavelengths at which you include the forcing, or even limiting close to the primary length scale on which you include it, or
To do what exactly with the length scale?
yeah, I mean, you can construct the same. You can get the same fractal dimension, not just limiting yourself to a delta function, so to a pointwise or a pseudo pointwise forcing, but including a fractal forcing, which takes into account multiple dimensions, or multiple not multiple dimensions, multiple scales. Yeah, multiple scales.
Yeah.
And limiting eventually the scale range you consider, not necessarily going to the larger scale, but limiting the scales you consider, but having a range kind of thing.
Yeah, I mean, there are many things. I mean, I thought of different things that, I mean, what I presented was the simplest and easiest to construct numerically that I picked. There are other ways. I mean, if I put a random walk in my domain and put vortices along it, that would also be a fractal dimension thing. A way to construct a forcing of fractal dimension. That's another possibility. I just found simpler what I did right now.
Yeah,
So,
that's
other possibilities do exist. I definitely will not claim it's the.
Yeah, thank you. Let's see if there is someone else who would like to ask a question. So I just invite the participants, in case you have questions, just unmute your mic and open your camera and ask the question, or maybe Alexandros, you can check if there is someone in the room who would like to ask a question.
No.
Okay. So to the participants, if there is someone who would like to ask a question from the chat, I can report it. Okay. So that doesn't seem to be the case. So if there is no one else in the room who would like to ask a question, I think we can stop here for today, and I invite everyone to thank Alexandros for the very interesting presentation which he gave today, and for the very active discussion which it has triggered. And thank you, Alexandros, for opening the seminars.
Thank you for being here.
Thanks. Have a good evening to everyone, and see you in 2 weeks.